Hello folks, this is the first of several tutorials that I'm preparing for performing multi-step finite element analysis in the 3D Experiences finite element module release 2024x. Now, specifically, I want to show how loads and boundary conditions must be propagated or uh, or otherwise through steps. I'll be discussing this for a three-dimensional element, break element, hex element, and let me go to the problem that I'm going to be doing, which is very simple. It's an actually loaded member, and I don't want to clamp the left side of it because then the stress distribution is not going to be uh, uniform through this thing. So what I'm doing on the left side, as you'll see in a minute, I will just leave it so that there is no local stress distribution. And on the right side, I apply either a translation or a, a force or pressure. on the on the left side, instead of clamping it, I use the so-called 1, 2, 3 rule. In other words, one point is completely fixed. This face is put on a slider, and this is prevented from moving upward, and therefore it cannot tip over. So when you think about it, what that means is that essentially this thing uniformly shrinks without having local concentration of stress. If I had clamped this end, I could have done the explanation in that context, but then you would see a very high stress concentration at the clamped area, which I don't want. On the right side, in these tutorials, I will either apply a pressure or a displacement or both, as you'll see. It's assumed that the dimension is 10 inches long, 1 by 1 square cross section. Young's modulus 30 times 10 to the 6 psi, 30 million essentially. And Poisson ratio 0.3. I could have taken, instead of 0.3, I could have taken 0, but I'll just leave it the way it is. Now, I want to show you when you apply a load of 3,000 pound psi on this side, why does it displaces by that amount? So essentially, we have a fancy spring, and the displacement is going to be force over stiffness of the spring. But we know the stiffness of the bar like that is AE over L. Okay, so this reduces to FL over AE. But we know what F is area times the pressure. And notice that the A drops out and you get PL over E. Now, P, assuming is 3,000 psi, L is 10 inches, put the E 30 million psi here, and you're going to get 0.001 inch. So what that means is that you apply a pressure of 3,000 psi, this end is going to displace by 0.001, or if you apply a displacement of 0.001, uh, the force required to do that is 3,000 psi times the area, but the area is 3,000 pounds basically. And this applies to either compression or tension. Now, how are these tutorials broken down? Tutorial 1, which is the present one, what I'm going to do is I'm going to do it in 2 steps. First, I apply pressure on the right side, 3,000 psi, to cause a tension, so that thing stretches, elongates. And then this pressure, if I don't do anything by it in step 2, is automatically propagated. That's how the software works. If you apply a force here or a pressure here in step 1, in the next step, this is going to be automatically propagated unless you decide to modify it or delete it. But let's not worry about it. Now, then I'm going to apply in step 2, this is pressure 1 is automatically propagated, but I also apply a pressure 2, which is compression. This is how I'm going to do this problem. And I will show you when you think about it, what that means is that you elongate it, and then the same pressure, except that's the compression, you bring it back to a position. So what we should get at the end of step two, we should get no stresses because it's going to go back to where it started from. Let me show you the tutorial two, what it's going to be. Again, I apply a pressure on the right-hand side, 3000 psi to extend it. And then in step two, I will let this pressure propagate just like the one above it, just like the tutorial one, but I will apply a displacement to that end that has moved, and the value of that displacement will be zero. And this is, I mean, obviously, this is essentially going to compress that, okay? You might wonder, why is zero going to compress that? You'll see that's the whole point of these videos. This is not intuitive, and I will show you what happens if you think that maybe you should have applied negative 0.001. I'll show you what happens. And these are the other tutorials, 3, 4, 5, and we do this thing as we go along. I will explain these things one more time as we go along for every single one of these tutorials, and this is why there's a duplication in some of these tutorials, the explanation, of course. I could have done everything in the same tutorial, which would have been maybe an hour and a half long, which I didn't want to do. Now, once I do this thing for you, tutorial one, then I'm going to come back, okay, how can I mess it up? First of all, before I tell you how can I mess this tutorial one up, uh, I have a single structural analysis case. I'll talk about that later. Now, what if we remove the pressure from that, for example, first step? We can do that. And when you do that, you will get at the end of the step two, when you apply that zero translation, you will get compression 3000 psi. And obviously, this is wrong. It's very easy to mess these up because this is one uh, case that I'm going to do for you in this tutorial. I'm going to remove this pressure and same condition, zero displacement. You see that it's going to get messed up. And same way we can mess up tutorials 2, 3, 4, and 5, as you'll see later on. But we'll discuss this thing as we go along. What is this business of one single structural analysis case? You may or may not have noticed is that when you are going into a structural analysis, structural scenario creation, it immediately creates a structural analysis case. And unless you have to, you just basically stayed there, applied the load and displacements and things like that. You probably didn't bother creating a second structural analysis case, but you can, as you'll see that in tutorial 6 for the playlist that these things are going to go into, which is tips on finite elements in 3D experience. So tutorial 6 in that playlist is going to be this business of two structural analysis cases. So let's go ahead and do our problem. All right. So on the vertical plane, I will sketch a square one by 1 inch by 1 inch. So this is 1 inch. This is 1 inch also. Exit and pad it by 10 inches. 10 inches. There we are. Let me apply material on it. tools, uh, create a material. I'll call it tutorial 1. These are all the same, but I will apply it anyway separately. Tutorial 1. Okay, let's wait for this to pop up. Tutorial 1. I'll put it on this part. Let me close that. And now I'm going to input my values. So let's go here, double click on this. Structures, abacus multiphysics, mechanical, elasticity, elastic, 30 million psi, 30, I can, 30 million psi to 30, 1, 2, 3, 4, 5, 6, Poisson ratio 0.3, or I can let it as 0, but I did 0.3. Good, pretty much it. Now we're going to go and go to structural model creation. This is where I do the meshing. It's fine. Empty FEM. Click on the mesh tab, and I'm going to do a sweep meshing. Sweep meshing. So I select the object, and the mesh size I put on 0.25 inches. So there'll be 4 in this direction, 4 in the Z direction, and I have 20 layers. So 20 layers to depth. Depth meaning the length. There we are. Okay, and then for properties, you click on the properties, click on the solid section, select your part body, so proper material is going to be picked, which is tutorial 1. That's it. Now we're going to go to structural scenario creation. Okay, now notice what happened. uh, First of all, I need to, this is a structural analysis that I'm doing, and then I created a mesh right there, and I say, okay, notice what happens is that right here, structural analysis case 1 is created. And for tutorials 1 through 5, there's only one of them. But tutorial 6, I will create a second structural analysis case in the same run. Okay, so for procedures, I'm going to do static step. That means automatically the nonlinearity is included, but basically this is to show you several steps through this deformation. So I'm going to change this thing, initial time increment 0.1, and the final time or maximum time increment 0.1. This is the minimum time. Okay. Now let's do the this end. Okay. Go to boundary conditions. So what we're going to do is fix displacement, this bottom left corner. I'm going to fix all 3 translations. Another one for this corner. I'm just going to prevent translation in the direction Z. And this is all on a slider. Okay, so one way of doing it, you just select the slider here and select this. There are other ways of doing it too. That's fine. Okay, good. So what are we doing? In step 1, if we go back here, in step 1, you apply pressure. So under loads, under pressure, select this face. And because you want this thing to be under tension, so minus 3000 psi, there. So I applied my 3000 psi here. Now, I need a step 2. I mean, obviously, I can run this thing, and it's going to run the step 1, and it shows you that this thing stretches by 0.001. Okay, but I'm not going to do that. I'm going to do it all at the same time. Step 2, we go here. So then you go and say another procedure, another static step. This is static step 2. Same thing, 0.1 and 0.1. Okay. All right. Now, I want to show you something here. Notice that there's my step 1. There's step 1. okay? And I applied a pressure. Now I created step 2. Notice that the pressure got propagated. Another way of looking at this thing, if you say right click, uh, what is that, feature manager, notice that pressure 1, these are the step 1 and step 2, what we're doing there. First of all, these displacements, fixed displacement and things like that, they're both steps, they're all propagated. But it's also this pressure that is propagating in step 2. That I want that. Okay? Remember, I said this is automatically propagated, maintaining a tension. Now, in that step 2, I'm going to apply I'm going to close that. In there, I'm going to apply a compressive pressure. So pressure on that same face. And because it's compressive, you have to put down 3000. Positive is always pushing into. So what happened is that pressure 1 was in step 1, made this thing stretch, and it's going to stay there. And pressure 2 is compressing it at the beginning of step 2, and we're going to run it. So let's go to simulate. First of all, let's do a model and scenario check, quick. Good. And now we're going to simulate. It's going to run both steps at the same time. I mean, consecutively, of course. First, it does step 1, and then it does step 2. The reason I made this thing geometric nonlinearity included, and then I put down initial time step, final time step, is because I want to get the results at different uh, steps of increasing the load. While this is running, I want to remind you that this is all in a single uh, structure analysis case. Okay, so you can see that some of the stuff, first 10 is for step 1, the next 10 is for step 2. Okay. All right. Uh, Instead of looking at the von Mises stress, I'm going to look at the uh, I'm going to look at the stress in direction 2, which is y direction, axial stress. So left double click on this. Under the stress component, you go over here, say I don't want the magnitude. What is that? Von Mises stress component. That'll do it. Stress component, okay? And that is going to give you the stress. Now, don't let it scare you. First of all, let's go to the first step, static step 1. Initially, there was no load. I applied a tensile load of 3000 psi, and I'm looking at the pressure. Notice that the stress increases. You can see that 300, 600, 1200, and it goes all the way to 3000. So this is the end of step 1. The stress should be 3000 because I applied 3000 pressure on the right side. Now, if you go to step 2 and you look at step, initial thing in step 2 is 3000. It should be because step 2 starts when step 1 ends. And then pressure decreases. You can see that because I'm pushing in the other direction. I'm pushing in the other direction. So when I reach the end of step 2, essentially it's all zero. Don't let this thing fool you because they're all to the power 10 to the minus 8. So they're all zero. This is all round off. This color is because of the round off. So this thing worked. Now let's go and try to mess it up. So I'm going to remove the pressure 1, which caused tension in step 1 from my analysis in step 2. So let's go back here. Let's go back to the scenario right there. If you right click feature manager, you see that? It tells you exactly what you have done. Here is the pressure 1, which goes through, of course, it starts at step 1 and it propagates to step 2. If I right click and come here and say remove pressure in static step 2, it's going to disappear from that. There's still the compression that we're going to apply right there, but we no longer have that tensile pressure. Tensile pressure is acting in step 2. This is what I'm saying right there. So let's go ahead and run it and see what we get at the end of step 2. Better be 0. Otherwise, there's something wrong. So you can run it from here, or you can close that thing and go and click it there. You can run it from there. Okay. Okay, it's almost done. Obviously, it doesn't bomb out, but let's see what we get. At the end of step 2, we are anticipating to get 0 stress. Do we get that? Okay. So let's close this. Let's close that. So this is step 1. At the end of step 1, obviously we expect a stress of 3000 because the pressure was applied 3000, stretching it. Now when we go to step 2, it starts at 3000, of course, because that was the last thing that we did in step 1. And then when we go to the next one, okay, it becomes lower. Very good. Very good. Lower, lower. And suddenly things go nuts. Of course, if you go out there, we will get to minus 3000. So what I'm saying is that we essentially get nonsense. We get the compression of 3000, which is not what you want. Okay, so tutorial 2 is going to be repeating the same problem. There will be duplication for those people who just jump into that tutorial 2, but there will be some duplication, maybe 5 minutes of duplication between tutorial 1 and tutorial 2, and I'm going to do it differently. Okay, good luck.